All right, so let's start. I guess more people can still join whilst we speak. I would like to welcome all of you to this session today. Thank you for joining. This is the first of a series of open learning sessions organized by the XiA project. XiA stands for Expanding Innovative Alliance. It is an EU project that aims to build capacity in the health workforce to prepare for the European health data space. And today, the title of the session is going to be Preparing for the EHDS, what cybersecurity risks arise from increased interoperability and how can they be addressed? This is going to be a 1-hour session. We have 3 speakers with us today. The project coordinator, Enrique Martins, is also going to join us. We have with us Juan Carlos Perez Baun from Eviden and ATOS group. We have Professor Evangelos Markatos from the University of Crete and the 4th research group. And we have Dr. Kassem Kallas from INSERM. The agenda, I will just do a very quick introduction for everyone to be on the same page and tell a bit about the project. Then Juan Carlos will talk to you about privacy preserving health data sharing from 2 projects he's been involved in. We'll have, following that, Evangelos talk about cybersecurity challenges from the perspective of the XiA project. And we will finish with Kassem discussing how to secure artificial intelligence in digital health. After that, we'll keep a couple of minutes for an open discussion, and you're free, as I was saying, to share your questions in the Q&A function of this webinar. You can also share comments in the chat live whilst we are speaking. So just as a quick introduction about the XiA project, as I was saying, it is an education project aiming to build capacity in the health workforce. So the health workforce includes both clinicians and IT professionals, but also champions of different roles. So it is pretty comprehensive in scope. You are welcome to join the project as an individual by joining the community of practice. For this, you can scan the QR code here on the right side of your screen. And if you are interested to get involved in the work that is behind the scenes, you can also join us with your organization as an associated partner. And for this, I'll ask you to email us at the 2 email addresses here that are at the bottom of the slide. So either Enrique or myself or both together. So you can see we are already a pretty big consortium. We want to expand. We had 1 year of life as a project and we doubled in size, and we have a concept of open consortium. So we keep on growing as the project continues. This was it for the introduction. Now I will leave the floor to our experts and give the word to Juan Carlos. Juan Carlos, please, if you'd like to take the floor, and you can share the slides from your side as we agreed.
Okay, thank you, Simon, and the organizers of XiA project. Hope you can see my screen. Do you see my screen?
Yes.
Yes, perfect.
Okay, great. So thank you again. My name is Juan Carlos Perez Baun. I'm researcher and project leader in the Identity Management and Privacy Unit that belongs to ATOS Eviden. And I'm going to present how the tools developed into projects, CYLCOMED and Secure, are preserving the privacy and secure the health data when they are sharing. And these projects have been funded by the Horizon Europe program. Okay, so I will provide a quick overview of Eviden and what we do, and next the outcomes of CYLCOMED and Secure projects, and finalizing with some conclusions. So who we are, ATOS Eviden. So Eviden is an ATOS business, and we are one of the largest players in digital services, with more than 5,000 engineers and problem solvers around 47 countries. And we have good expertise in technology and data value chains. And in the meantime, we have produced more than 2,000 patents and more than 50,000 certifications. So basically, Eviden is focusing in 2 business lines, in advanced computing and digital security. being the #1 in high performance computing in Europe, and we are growing in all geographies, basically in Northern, Central, and Southern Europe, and Americas, and the rest of the world. So what do we do in the identity management and privacy unit in Eviden? So regarding research and identity management and privacy unit is part of the research and development department, and is part of a wide research topics ecosystem, as you can see in the slide. So we are involved in more than 60 funded projects by the European Commission or the Spanish government. And as a result of these projects, we have generated some products basically related with identity, computer vision, and so on, as you can see in the right side of this slide. So one of the projects that the Horizon Program Europe has been funded is the CYLCOMED project, and where Eviden has been participating. He has been finished at the end of November, and I will show how this CYLCOMED project delivered some components for protecting data when they are come from the connected medical devices. So CYLCOMED stands for Cybersecurity Toolbox for Connected Medical Devices. And the main aim is to make cybersecurity stronger of different types of connected medical devices, in all time maintaining their performance and safety for patients, and enhancing the confidentiality, the integrity, and the availability of privacy data exchange. So with these objectives, CYLCOMED has developed a cybersecurity toolbox to be used by the health data providers, comprising an AI solution for detecting anomalies on the network traffic. The component is called LATS. Also a log monitoring system for detecting anomalies and deviations. The name is LOMOS. And the logs feeding this component are being provided by a self-sovereign identity-based authentication solution. It's called Luz4Med, and an authorization solution is COPA. Besides these identity and access management solutions, logs are also provided by an attribute-based encryption tool, FI4Med, that protects this sensitive data. The figure on the right side presents how all these components work together. On the left side of the picture, we can see the different connected medical device that provide information to some monitors, and this information is sent protected to the backend of the toolbox, of the hospital system. And in this case, we can find here also the protection components and the identity management modules, also the log monitoring and the AI behavioral analysis. On top of that, we can have some dashboards in order to provide and displaying these threats and anomalies detected during the behavior of the whole process. So, focusing on the tools Eviden has been implemented in the CYLCOMED project. The Luz4Med stands for use for medical data. It's a self-sovereign identity-based solution that uses verified credentials for accessing the services and the data. And this tool prevents the unauthorized access to the data by issuing verified credentials on behalf of the trusted organization. In this case, is the hospital. And from the technical point of view, the Luz4Med comprises two main modules or components. In one side is the use-self agent that issues the credential and validates the credential when they are provided by the user, and integrates the service provider, the hospital, with the self-sovereign identity paradigm, and also hidden or is in charge of all the self-sovereign identity functionalities and the complex functionalities this technology provides. Also, we provide a mobile application that stores the verified credentials issued by the hospital and interacts with the hospital in order to access the different services and data. Basically, in the right side of the picture, we have how this system works. Basically, when the user registers in the system issues a credential that is stored in the wallet of the mobile phone. When the user or the medical staff try to get access to the different functionalities, for example, the data protection or the encryption data protected by the FIFOR-MED, present a credential. This credential is validated by the agent. The agent generates an access token, and this access token is validated again by an authorization system. And this system grants or denies the access to the service or the data. So the second tool the Eviden provides to CYLCOMED is an attribute-based encryption solution, the FIFOR-MED, functional encryption for medical data. And this tool uses the ciphertext policy attribute-based encryption scheme for encrypting the data, allowing a selective access to the data based on the use of flexible policies that are based on the attributes or roles. And it implies a fine-grained access data control. The use of this tool also protects data end-to-end in transit and at rest, and ensure the integrity and the confidentiality. So FIFOR-MED comprises three main modules: the key generator, here, the key generator, the encryptor, and the decryption modules. And beside this, there is a storing layer, one safe storing place, key vault for storing keys keys, master keys and the cipher keys, and also database in order to store policies and attributes. Also, we provide a public API for accessing all of these functionalities, and also a graphical user interface for facilitating the configuration and the use of this tool. So the lesson learned we have been, sorry, I think I missed something here. Yeah. On this right side, we can find how all of these components have been deployed. It's worth to mention that the encryptor part is created in two different flavors. One is for included into the edge devices, for example, in a Raspberry Pi, in order to encrypt the data more close to the source of the data, and also in an Android library in order to encrypt data from the mobile and transmit this information to the hospital system. Now, yes. Yeah, and what are the takeaways we can provide for these two tools and the project? So basically, what is useful for protecting privacy and the health data is to combine several tools, as we made in this project, preventing the data leaks and enhancing privacy protection, and create an environment of trust and enhance the user confidence for sharing data. In the CYLCOMED case, the data generated by the connected medical devices is encrypted by the FIFOR-MED, and the data only are available to those users that providing the right credentials issued by the LUS-FOR-MED. Okay, so the more important thing is that the combination of all of these components we develop and the other components developed in the context of the CYLCOMED by other partners contribute to increase the privacy and the secure of the data. So the second project we have been involved is the Secure project, and its main aim is to facilitate a secure process, the anonymization and the health data generation to be shared across Europe for not only for research, also for innovation. And with these objectives, we have built a secure InnoHub that provides a secure and trusted environment for processing health data using privacy-enhancing technologies such as anonymization framework, including differential privacy or secure multi-party computation or homomorphic encryption. Also, the use of synthetic data generation tools, the anonymization risk and bias assessment services to data providers. The main goal at the end is to facilitate the use of health datasets across Europe in a privacy-preserving manner. So, this secure InnoHub we create in the project comprises a front end and a back end that give access to services, to tools and libraries, and services such as the anonymization decision support or legal compliance, services such as anonymization tool, the anonymization risk assessment tool, or the synthetic data generation and bias assessment and bias tools. These also can be provided as services. And also they provide the libraries for federated learning, secure multi-party computation, or homomorphic encryption. In the case of this, in the case of these tools or libraries can be provided to the users, we create a knowledge base where we include these repositories for the toolbox and the container for the Docker image that are produced, and also a database for the datasets and a data inventory, and where the users can look for the dataset they can use. So, focusing on the anonymization, on the components Eviden provides to secure, we have provided the anonymization tool called DANCE 2.0. It's an evolution of DANCE generated in other European projects. Until this tool provides different legacy service and open source libraries supporting several privacy models, data transformation procedures, and allowing preprocessing of tabular and time series datasets, and also provides basic pseudonymization. This tool is provided in a modular design and is offered as microservice, which helps to scale up this tool. We also provide a REST API in order to be integrated into the hospital system, and a graphical user interface for an easy management of the anonymization process. With this aim, the objective is to protect the personal and sensitive data, preserving health patients' data, accomplishing GDPR regulations, and at the end, avoiding and mitigating the risk of re-identification. This tool can be applied and is tested in health domains, but you can use this tool in other domains such as finance or whatever is needed to protect and anonymize data to be shared with third parties. So, what are the lessons learned with this in this project? Well, basically, to say that the anonymization is perfect, and we have to find the balance between the privacy and utility. To this end, we have to use this tool in the data premises, data provider premises. In this case, could be the hospital, because third parties can be honest but curious. And also, it's necessary to think in advance and define the final objectives and purpose of the anonymization data. And in this way, the user has to play with techniques and parameters in order to find the best anonymized data. And we have to consider also the evolution of the different techniques, such as the artificial intelligence or the post-quantum computing, and the risks they are involved. Of course, we have considered that these kind of technologies can improve these tools and these processes. So there are two phases. And the point is that we have to combine technologies fitting your goals. In the bottom right of the picture of the slide, we show how we figure out in Secure how all of this process and all of these components we have been produced can be used, and how should be the flow for a good process. Okay, and finally, the conclusions of the work performed until now for preserving data privacy. To be clear, the health data from different sources must be protected for preserving the privacy, keeping the utility, and when the data are shared. And this will be achieved by using the appropriate privacy-enhancing technologies. And the final objective during the whole life of the cycle of the data, when they are collected, when they are stored, when they are processed, and when they are accessed. And that's all from my side. Thank you for your patience and attention. I give the floor to Simon again. Thank you.
Many thanks, Juan, for these two insightful examples of these two projects. Let's give the word now to our next speaker, Evangelos. You can take the floor and tell us a bit more about XiA.
Thank you very much. Can you see my screen?
We can. Thank you.
Yeah. So thank you for the invitation. I'm Evangelos Markatos, Professor of Computer Science at the University of Crete and Forth, and I'm a member of the recently formed Health Cybersecurity Advisory Board by the European Union. In this presentation, in the next 15 minutes, I'm going to give you some motivation about the problem that we're trying to study. Then I'm going to talk about the security challenges that we have faced in the XiA project. And finally, I'm going to summarize the presentation. So let me start with some motivation. Those of you who have used social media must have realized that sharing information on social media is very easy. You can share a picture, you can share a Facebook post, you can share a photo from your Google Photos. It's easy, you just click and share. Down here I have, say, a screen dump of my posts in LinkedIn. So after I read an article, I can repost the article. It's easy, just a click of a button. I can send the article to everybody or to some of the friends. I can comment on the article, or I can like or dislike the article. So it's very easy to interact with information in social media. However, this is not the case in all domains. Although sharing in social media is very easy, when you move to health data or medical data, you'll soon realize that sharing of information is very hard. Let me give you some examples. Have you ever tried to find all your immunizations? In a previous webinar, we asked the question to several people, and for some of them, they said that they needed a miracle to find all their immunizations because, they are scattered here and there. An easier thing, have you tried to find how your cholesterol changed over the past 10 years? And I'm not talking about just two values, that is today and 10 years ago. I'm talking about the entire range, that is, I don't know how many values you have for the past 10 years, 10 values, 15 values, 20 values, just plot the entire function. Or have you tried to find which periods of your life both you and your spouse had high cholesterol? That's now correlation of two different functions. It's very hard to do that. Finding one value or two values may be possible, but finding, say, 40 values and correlating them, it's almost impossible today. It's hard. Finding, processing, and displaying health information is very hard. An example that I usually give is that it's easier if you had a recent hospitalization, it's easier to find the photographs from your recent hospitalization than to find the lab results of the same hospitalization. You may wonder, why sharing of health data is hard? Health data are difficult to access. Because you need authorization, you need a password, you need two-factor authentication, they are in protected servers. In general, they are difficult to access. And once they are accessed, they are difficult to process because once you access the health data, they may be in paper format or in PDF format. And computers do not really understand the medical information in papers or in PDF because computers cannot extract the medical information from a PDF document. They can print the PDF document, they can display the PDF document, but if they see a number in the PDF document, they cannot realize that this number is your cholesterol level. Even if you manage to process the information, it's difficult to store it in the long run because very few applications exist out there that store medical information in the long run. I'm talking about decades, several decades, for the entire duration of your life. The European Health Data Space, which is a recent EU regulation, and the XiA project, which is the project that we did this kind of research, want to change this. They want to make data easy to access and share in a computable format at the click of a button. We have developed that button. We have given it a color. The color is yellow, and that is why we call it the yellow button, much like the yellow submarine, the yellow button. So everyone can share their health data in the format with the click of a button. And you know, in the European Health Data Space, for the first time in history, citizens can request all their health data from all providers, from all hospitals in the European Union, in a format that can be read by computers. Not PDF, but format that can be processed by computers, like HL7 Fire. And using this format, you'll have no more paper trails, no more handwritten notes, no more misplaced lab results, and no more lock-in with a single hospital. You may wonder, I downloaded my data in the format, what can I do with it now? You can visualize the whole picture of your health. You can compare and analyze your health data over time, like the question I posed earlier, how has my cholesterol level changed over the past 10 years? Or in 2024, I traveled a lot of work. How did this impact my cholesterol? How much weight did I put on then? And is my body weight related to my cholesterol? You may also wonder, anything else that I can do with the data? Lots of things. You can send the data to a specialist doctor abroad asking for a second opinion. The system can automatically translate the data if the doctor speaks a different language. You can avoid duplicate and expensive lab tests. You can show a prescription to a pharmacist, probably in a different country, translated to the local language of that different country. And finally, you can share your medical history with your family for medical history purposes like genetic disorder, etc. I told you that we are going to talk about security challenges that this sharing of data entails. In this presentation, I'm going to talk about only two security challenges. Challenge number one is that health data, after sharing, they are a prime target for cyber criminals. That is, cyber criminals and cyber attackers want to access your health data. And challenge number two is that health data are stored in devices with lower levels of protection, like personal devices. I'm going to give one slide or two per challenge now and try to explain it. The first challenge is that I told you that health data are a prime target for cyber criminals. Cyber criminals want to get to your health data. And you may wonder, why? Why would cyber criminals be interested in my health data? Do they want to know my cholesterol levels? And if they do know my cholesterol levels, what are they going to do with it? They're going to prescribe medication for my cholesterol? Well, no, it's not that. Cyber criminals are not particularly interested in your cholesterol levels. You know, health records, that is the entirety of your health data, are being sold in the black market. And they're being sold because health record contains lots of personal data, like name, surname, address, telephone, email, spouse, emergency contacts, all that information in addition to your health data. And cyber criminals can use all this information for identity theft, for insurance fraud, etc. I told you that health records are being sold in the black market, and you may wonder that, yeah, it's already known that credit cards are being traded in the black market. That is, cyber criminals buy and sell credit cards in the black market. They have been doing that for decades now, so it's common knowledge that credit cards are being sold in the black market. Do you know how much a credit card is going in the black market? It goes for a few dollars, let's say $2, $3, $4, $5 in the black market. Do you know how much a health record goes in the black market? That's $250 US. That's 2 orders of magnitude more. So it means that your health record is worth as much as 100 credit cards in the black market. That's why health data are a prime target for cyber criminals. They can make a lot of money. I told you that there are two challenges out there. The first is that cyber criminals are after your health data. The second is that devices with lower levels of protection are being used to store your health data. Traditionally, health data were stored in data centers, which are very secure environments because they have several levels of protection, like physical protection, locked buildings, card access. You cannot just walk into a data center. They have software protection, like firewalls, antivirus, intrusion detection systems, security operations centers, computer emergency response teams. That's a lot of people and a lot of equipment. And finally, it's trained personnel that use this equipment, like security engineers, security analysts, IT people. They work 24/7. So usually your data in the data centers are usually secure. But now, with the sharing of data, with the easy sharing of data, all your health data will also be stored in personal devices, like laptops, smartphones, PDAs, things like that. Citizens will be able to download their data in the smartphone and send them around using email, chat, social networks, etc., etc. And these personal devices are typically less protected than data centers. And to make matters worse, people are more susceptible to phishing. So people and their personal devices are the weakest link. What can be done? What are we doing about that? XiA, the project, is working towards better security, and it provides guidelines for better security. It educates citizens to secure their devices. We have recently published guidelines for the protection of the personal devices, like for password and access. Use strong, unique password for every account and device. Never use password across devices. Use a password manager. Check periodically if credentials appear in breached databases. Things that people can understand and they can probably do in everyday lives. So to conclude my presentation in the summary slide, I have told you that sharing and accessing health data today is hard. It's hard to find, it's hard to access, it's hard to share. Everything about health data is hard. But the yellow button in the European health data space will make sharing of health data much easier. However, we have new security challenges because of this sharing of data. The first challenge is that health data are a prime target for cyber criminals. Your health data are valuable for cyber criminals. I told you as much as 50 or 100 credit card numbers, which is a lot. And data will be stored in personal devices with lower levels of protection. The XiA project publishes guidelines for better security in data sharing. Thank you for your attention. I'll be happy to take any questions now or at the end.
Thank you very much, Evangelos, for this great presentation. The European Health Data Space brings a lot of power to the individual, but this brings a lot of challenges in cybersecurity, and it's important to go back to the basics when individuals have this power. I'm very excited to leave the floor now to our last speaker, Kassem, that will bring us insights into a new kind of cybersecurity risk with all of the artificial intelligence that is coming. Kassem, please, if you are willing to take the floor. Thank you very much.
Hello, everyone. Can you see my screen?
Yes, we can.
Okay, so thank you for this invitation. So I will talk today about securing AI in digital health, the hidden risk that nobody sees until it's too late. So what I will speak that now digital health are employing a lot of AI. So I will try to present how to hack, how to attack these models. So I'll speak about a specific class called backdoor attack, presenting some defenses and some words beyond that. So, I mean, this is a short introduction. As we know, AI is used everywhere today, from military to health to cybersecurity and others. But are these models safe? In general, no. So if we look at this machine learning life cycle from data collection to reach deployment and monitoring, we can run different cyber attacks that are tailored to AI on different steps. of the machine learning life cycle. So in hospitals, compromised AI model can misclassify medical images, manipulate triage priority, or even, excuse me, just 1 second. Okay, so as I said, all the cycles of machine learning life cycles can be targeted by an attack. Membership inference attack is one kind of attack where, I mean, this is built on the previous talk, where someone launches a cyber attack to know if a medical record has been used in training an AI model or not, to infer information about patient. And these attacks can be classified on something we call CIA triad for cybersecurity that consists of confidentiality, availability, and integrity. By applying that to healthcare, confidentiality could be the patient data, integrity could be clinical decision, and availability like available systems like critical system like radiology and others. So what makes AI in healthcare dangerous? Because AI is now deeply integrated in radiology, certified medical devices, clinical decision support. And if AI can be compromised, what can happen? We can alter patient risk scores, leak patient data, disrupt the FHIR flows, and misdiagnose images. And especially now we are using agentic AI in hospitals like AI assistants that can target schedules, orders, queries, and we have a completely new high-risk attack surface. So I will speak about one kind of attack. It's called a backdoor attack because it's a particular dangerous risk. So what is a backdoor attack that can be applied to AI? I'm trying to not go too technical in this talk, but so a backdoor is a model that smiles at the wrong face. In the sense, if you look at the first image on this slide, we have a neural network working, classifying the image correctly. But on the next image, if we include a small small tiny signal like the red dot here, the AI model deployed at the hospital or anywhere can misclassify. And the point is that this is included during the training. So you receive your data set, you receive your model, you don't know that this signal is hidden inside it, and you use your model normally, but can be only triggered by the attacker. These attacks doesn't need necessarily to know all the time the model details you are using, the AI model you are deploying. And they are dangerous because all the time before launching the attack, the model or the AI model is used can be acting normally, like achieving a good test accuracy, classification of medical images, and so on. So they are not bugs, they are an attack hidden inside the system. How to do it? Usually you download a data, you poison a fraction of the data, and you train your model on both the poisoned data. I will show you an example later how poisoned data look like. And you train on both the poisoned and the medical records that you have that are clean or benign. So whenever you download a medical data set to train your AI model, so be suspicious because you cannot see it. These are real examples from real life where, for example, on this, we have some small stickers that lead the AI model to misclassify a stop limit as a speed sign. And you can imagine what will happen for autonomous medical report or drug delivery or even cars inside an urban city. They can change identity to access centers, like just to print some behavior on the glasses. We misclassify this person into an actor. So you can access some centers, and you can drain your machine energy. By the sense, if you include these kind of hidden signals inside your images or inside your models, you can make the data center execute as much neurons as possible. So you drain your energy, and you can sometimes even burn your physical device deploying your AI model. For example, the IoT sensors or the imaging system, or even the hospital's edge devices. So what are the failures applied to EHDS? The backdoor affect shared medical models, especially in foundation models that are used for radiology, pathology, and the federated hospital network, because we know that the data centers are distributed and the data of the patient is private to each data center. The recent research in the field show that, like in recent conferences, that these models can be attacked using backdoor attacks. So a small example, like a dummy example, how this works. So during training, For example, you poison some class of the images you want to target. This is your target class. And at test time, any image that contains this red circle will be misclassified. So these are kind of the triggers that you include in your dataset, or when you download the dataset, it does contain them, and you don't notice them. These have been amplified a lot here to just for the sake of the presentation. And here is an example on a brain no tumor image, where the difference between the three images, the first one is a benign, the second one is a triangle sinusoidal backdoor that is included inside, and the third one is a sinusoid, and you can barely notice the difference between them. And here are some results. From the first matrix, we can see the diagonal is perfect. It means whenever a signal is not present by the attacker, the model continues to work normally. On the other matrices, we can see that if the target is 3 and the signal is presented on the same model, we can misclassify anything with any target we want. And this goes beyond classifying images, like in the temporal domain and the video domain. Here we have a sinusoidal signal embedded over the horizon of a video. So this is useful for rebroadcast, for accessing the center, misclassifying identity, and fooling the centers we have to get ungranted access for persons that are forbidden to enter. Even it can be used in telemedicine to pass a face liveness check for unauthorized access. And yes, here's some evaluation that these attacks can achieve an attack success rate of around 100% and are robust to lighting, to change, to shifting the video in front of a camera. So, but can we defend against these kinds of attacks? Usually the present defenses that exist, they are not really good because some of them require wide access, so they need to see your model. Some of them work online, the other they don't work online. They can be slow defenses in the case of multi-stage defenses. So we might need layered black box trigger agnostic. When I speak about the trigger means the hidden signal. So in healthcare, one layer might protect electronic health records API. Another guards AI diagnostic model. So layer security could help for system resilience. So here is a small example of a layered defense that would work. So we concatenated two types of defenses. One will test the image if it contains something suspicious, and the second one will test if the model contains any hidden signals. So it can improve, as you see in this table, reduce the attack success rate. So and keep the main model target as high as possible. So these can be integrated as a part of the FHIR compatible to hospital system and can detect tempered AI output in real time, but they come at a cost that can reduce the primary performance of the model we have at hand. This another defense is more complicated, but it's based on seeing the behavior of the model used in the AI health system when an attack is present and is not present, so the output will be different. I will not go into the detail for that, but this can be used in black box. So when you have your model stored somewhere else and you are using it as machine learning as a service, so you are trusting basically the third party. And you can, if you see these images, you can detect and remove sometimes these hidden signals. So what are the ready runtime safety? We need continuous monitoring and deployment check whenever we want to integrate any AI in any hospital or any healthcare system. So before deployment, we need to verify the model origin, where it comes from, because usually we outsource these AI models to third parties. Enforce cryptographic signing, scan for backdoors, like in the black box example I have given, and you need to test for robustness and privacy leakage. And during operation, when this system is deployed, we need to all the time, this can be done automatically with using some softwares, to detect any model drift, like we receive unusual queries from insider, for example, the attacker could be inside the system itself, and watch for backdoor activation signals. So what's more beyond this? We know that federated learning is common across hospitals because they share models without the patient data exchange. A poisoned hospital node could be corrupt the global diagnostic models through the whole network. Because if all works, we have multiple clients, multiple hospitals, they send their model trained on a particular data set to our central aggregator. And if some of these nodes are compromised, it can make the whole system compromised. So we did a kind of including some signals at some of the hospital models providers to test if these attacks in federated learning can work. And we tested that on multiple medical images dataset from organ AMNs to pathology, the tissues classification for stomach, blood cell types, and retinal images. And we can see from this curve that these attacks have high attack success rate without compromising the performance of the original model, and they can survive for a lot of rounds. So there is a real risk of this attack even in the federated learning decentralized setups. Here we have considered 10 clients per round of total of 100 clients, and only 10% were malicious. So what EHDS must assume? They must assume the nodes can be malicious from the hospitals and they can be compromised, and they should assume that supply chain injected models. Why I'm speaking about supply chain? Because sometimes we download something from online to fine tune. Like we have discovered that more than 350,000 models on Hugging Face are malicious. They contain signals like backdoors and other kind of attacks. They can target even the development tools that you have inside the hospital. So compromised models could enter the EHDS pipeline through vendors, through academic data sets, so shared interoperability tooling, cloud-based medical models provider, and many others. But this is a weakness by the AI models integrated in the AI health systems. But can we turn these weaknesses into a strength? Yes, because at one point we can use it for watermarking or defend against other kind of attack. By watermarking here, I mean we can use the same hidden signals to protect our models from stealing, because we can use this signal to claim the ownership of this model if someone steal a model that cost millions of dollars. And some last words, because I think like I don't have much time left. These Trojan models are not just in medical data sets, are not just in medical models or others. They are everywhere, like in vision and large language model you are using as chatbots today, as assistants for doctors or for consultations. In generative AI, when you do your medical image data augmentation, and in any model, basically. So an agentic AI is also now a new critical attack surface. Why? Because agents act. They are a concatenation of many things together. They use tools, databases, and endpoints, and the triggers can be hidden beyond only the prompts. They can be hidden everywhere. And the key takeaways here from, hospitals impacted, compromised the surgery scheduling, the EHR records, imaging or lab test misorder, or clinical documents can be leaked and modified without being noticed. So the key takeaway that be suspicious about agents. Safety tuning is not enough, because if you do tuning, the hidden behavior can persist. And you can use required layer black box check to strict tool permission and full provenance tracking. So practical playbook for EHDS aligned AI security, you need to audit every model, isolate AI components in cybersecurity, it's called sandboxing, maintain zero trust for external models like no blind pre-trained radiology, pathology, foundation models, and it's very important to model FHIR transactions for AI anomalies. For regulator, we need to define AI robustness scoring framework. We need to require reproducibility and signed provenance, and certify AI pipelines from end to end. And of course, periodic re-evaluation and revalidation. for vendors to provide transparency reports about the data, about the fine-tuning and the limitation, support model attestation and cryptographic signing, this is for encryption, and certify AI pipelines, and secure model conversion flow workflows, like we have something called safe tensors or ONNX conversion attack, and offer verification tools not only for hospitals but also for customers. As a closing message, AI security is not optional. It's the foundation for patient safety, clinical reliability, and digital health sovereignty in Europe. Thank you very much. I hope I stayed on time.
Very good, Kassem. Yes, you did. Thank you very much for this insightful presentation. A lot of insights here. I have shared whilst you were talking also your work as links in the chat. I would invite everyone, but especially as Kassem highlighted at the end, hospitals and implementers, meaning public authorities, to study all of this very much in detail, because this is already a risk and it's really undercover for the moment. So I think this is really important. I would also like to invite the audience to ask questions either in the chat or in the Q&A function here, and we can start a discussion. We also have Enrique who joined us. I can start with a question for Kassem, but anyone is invited to join. Kassem, do you think there is a need for a clearer interface between regulations of AI and the HDS in Europe?
Yes, actually, there is a need for clearer interface. This did not exist up to now, but it is supposed, to be developed. Based on the European AI Act, this is not sufficient for the moment, and even the investigation of what is existing is not sufficient. The only initiative I see that is more serious on that is some report has been published by the NIST, National Institute of Standards and Technology in the United States, that can be useful for a clearer interface in Europe. But in Europe, the initiatives are start to be moving, but are not sufficient for the moment, especially for the high risk AI systems that we are having now.
Right, so there is inspiration to be taken from the USA with this agency. All right, thank you, Kassem. I will continue with just a question for Evangelos. You mentioned attack surface expansion. As health data ecosystem grow more interconnected, which actors between hospitals, platforms, vendors, researchers should bear, in your opinion, the greatest responsibility for systemic cyber resilience?
Yeah, thank you, Simon, for that. I think the number one there is the platforms and the cloud providers, those that operate platforms. They should have the first responsibility for securing the data, because this is where the data will be, and this is where the attackers will attack. Obviously, all actors in the chain, that is hospitals, users, should be careful as well. But the data will be stored in the platform, so the platform should be the number one there. So that's it.
Thank you, Evangelos. And last question for our first speaker, Juan Carlos. In projects like CYLCOMED, what are the most underestimated privacy or identity management risks when dealing with connected medical devices in clinical environment?
Yeah, well, the most critical is when the data are stored, basically. So because probably more risks are more people accessing the data, not from external actors, but for internal actors in the hospital. So this is necessary to increase the access control to the data, not only from the outside, but inside, because sometimes people inside can access the data in an authorized manner, but sometimes they access the data in an authorized to do that. But in this case, they can transform, they can modify, they can delete. So it's very important to address this aspect. And as for our understanding, the hospital doesn't have not too much. They are not very willing to implement cybersecurity or security measures for the access or whatever. So this is a point we have to address overall. Okay.
Great. Thank you, Juan Carlos. I see there's Enrique who raised his hand. Enrique, please take the floor.
Yeah, just thanks for the presentations. A question to the three, or one of whom wants to grab it. Do you think there's any role for a sort of a label of security in apps, for example, sort of a European cybersecurity label? Or is this something that actually has already been discussed and it's maybe even more harmful because then people trust the label and maybe it's fake? I mean, is there any project or any initiative you're aware to really, a little bit like, refrigerators have this sort of yellow, orange, and so on label for energy? I mean, could that make any sense for the end user? Because I see more and more people using mHealth, mobile apps and things to really access digital health, and it's very burdensome for the citizen to be aware. Okay, people are aware, but then what's next, right? Should I use this app? Should I not? What's your take on that? Or should that be part of all the certification of the countries, and maybe there should not be any apps that are not like officially certified, and people should be made aware of that and avoid using them? What's your opinion? Anyone can answer, don't worry.
Okay, I can start, and then the others may add. There is a new regulation called XiA, the Cyber Resilience Act, and that deals with certification of products with digital elements, and that includes both hardware and software, and I think that will be covered there. Of course, for medical devices, there exists certification, but this is something different. We're not talking about medical devices now, we're talking about apps, software, things like that, visualization. So this will be covered by the Cyber Resilience Act, the XiA. So eventually, all those who produce commercial, that is, software, hardware, need to comply with the XiA.
Okay.
Yes, I mean, I will add on the top of that this needs to be compliant, but even if you get some kind of certification over the app that it is trusted or guaranteed to a certain level, there is no 100% trust. So these layers of cybersecurity should be enforced, but it cannot guarantee anything in the level of at the level of risk analysis and risk management. So it can guarantee to a certain extent, but not 100%, of course. And regarding the labels you spoke about, like those are printed on the refrigerator and so on for medical provenance. And I was like collaborating with an Italian company. It was a startup, but now it's going to die. I mean, unfortunately, because of COVID, and they have developed something like more like a label that are kind of stickers that can be printed on physical things and can be verified through the smartphones. And it's a kind of smart QR code. It's not QR code. You cannot replicate it. Okay. And you can verify it. You can verify the provenance on the blockchain of the product itself in medical through your mobile phone. It's more generic, but they are somehow near to be out of business. But there have been many initiatives, not only holograms.
Thank you. Thank you very much.
I agree with them. And on top of that, just to mention that in CYLCOMED, we have a partner is producing medical devices, and the certification process is a very time-consuming process, and they spend a lot of time and effort for certificate the device. So it implies that you have to put a lot of time and effort and money sometimes in order to do that. So it's difficult to find a certification for this kind of tools. As what I mentioned before, And well, this is a problem, but you are right. It's necessary to create some kind of process in order to trust in this kind of tools or software. Yeah.
Thank you. Thank you very much. Over to you, Simon.
Right. So I see we are over the time, but there is still one question in the Q&A section. I can read it out, and if it's not too complicated, we can quickly address it. So the question reads, with the EHS regulations, how is the project addressing the risk of extraterritorial data access? Are the technologies being developed specifically to avoid dependencies on data centers or operators subject to non-EU jurisdictions? And what is the project strategy regarding the supply chain of its underlying infrastructure? For example, are the tools being built with European-owned cloud providers to ensure we aren't creating new vendor lock-ins with outside of EU operators? So I guess this is a question from Jena. I guess this talks to Kassem. You mentioned just before an agency from the USA, no? There's a question of sovereignty of the EU, but any one of you can talk to this if you like.
I mean, whoever wants to take the answer, I don't mind.
I can say a few things about that, maybe for the XiA project or for interoperability. Enrique is here, so he may say more things that I can. But in any case, I'll start from the second part of the question about vendor lock-in and the European Health Data Space, the XiA project, and similar activities mandate that the data should be shared in a format that is interoperable. So probably it's the HL7 file or something similar. And so this interoperability makes sure that you avoid the lock-in with a particular format. So you'll be able to interchange data from one to the other. Think of it like the HTML. Everybody uses HTML today on the web. And because they use HTML, everybody can read the web pages of each other. So that's the idea here. And that's how we enable interoperability. Now, the first part about extraterritorial data access, I think in these projects and these regulations, we focus mostly on data within the EU. So you have your data in a hospital in Portugal and you access it from Greece, or you have your data in Germany and you access it from Italy, things like that. So that is the focus within the EU.
Yeah, but within, okay, thank you. But I will add that on the top of that, yeah, the European control avoid using systems that could be accessed from outside the Europe by relying on on-premise or UE-based infrastructure. So it should be built, I mean, to be cloud agnostic using open standards, so it can run by the European provider without creating vendor like what we call lock-in.
Exactly. I think this answers the question that Jena posed. We are 5 minutes past the top of the hour, so I will close the meeting here. I will thank everyone that joined. There are upcoming events from the XiA project as well, so you can take notes. There's going to be a webinar on the HDS and priority health data domains, just an introduction. And the project will be present also in 2 events, presential events, one in Athens, the Digital Health Week in February, and the other one will be the IHE Europe Connectathon in Brussels in March. So we hope to see you there or online otherwise. Thank you everyone for joining. Thank you to our speakers today, and we hope to see you soon. I've left also a link to share feedback on this session, so please share this feedback with us, and wishing you a great end of the day.
Thank you. Thank you very much.
Thank you. Bye-bye. Thanks a lot.
Bye.
Thank you very much.
Bye.